Hi, welcome. Let's do some math. Today we'll talk about the third, the final conic section that we're going to be talking about. Here's a little, this is a little kind of diagram of each of the conic sections. Some people say circle and ellipse are different conic sections. I personally think that they're pretty different. An ellipse is just a circle that has something called eccentricity to it. It's basically a stretched out circle. A parabola is one of the most familiar ones. And then the last one, which is probably the least studied, I don't know, I don't think it's any more weird than the other ones, but a hyperbola. And you can kind of see, so what it means to say a conic section is how a plane, like not an airplane, but like a flat plane would intersect with stacked cones like this. So in each of these drawings here, you see that there's a plane that intersects, and the cross-sectional area that's like created by that intersection plane is the shape. So we're going to be talking about hyperbola today. Um, and here's a picture of something in the world that is a hyperboloid, a 3D like rotated parabola, hyperbola. That's like a cooling tower for a power plant. It's a gigantic structure and is made in this way to facilitate airflow, and because it's one of the more efficient ways as far as building materials go, to create like a big tall hollow structure that way. Here's another one. This is the Kobe Port Tower in Japan. I think what's cool about this is it's just very counterintuitive, kind of, to look at a thing like this and think that there's only straight members in this structure. In fact, a hyperbola is pretty crazy. This line that I'm drawing, it is perfectly straight. I can't keep drawing it behind there, but if it kept going, you gotta imagine it's like angled backwards. It would go and do something like that. And there's just a whole bunch of those stacked up and angled in such a way that it creates this shape. And so this shape with these like opposing, it almost looks like opposing parabolas. It's not. That's what a hyperbola is. The geometric definition of a hyperbola is pretty weird. It's the set of all points in a plane such that the absolute value of the difference of the distances from two fixed points called the foci is a constant. I'm just going to draw something, and then I'm going to I'll pause the recording. I'll draw something and start the recording, so you'll see something drawn on this, and then I'll explain what I did. Okay, so I drew something here on this graph, and I'll explain what it is. The purple lines here represent the hyperbola. We have sometimes, like when we talk about hyperbolas in the real world, we're talking about a hyperbolic thing, but there's not two branches. So this hyperbola here has two branches, a left branch and a right branch. Or if a hyperbola is oriented vertically, it would have an upper branch and a lower branch. But it's possible to have just one branch. But this one has two. So the purple line is the hyperbola. The curve is hyperbola. The orange dotted lines represent what's called like it has a lot of different names. We call it like the Hyperbola Box or the Hyperbola Box, and we use that basically to guide our drawing of the graph. But we can also use it to conveniently label a few different things, and so that's what I'm going to do. Like all conic sections, there's like an HK involved in this one, and the HK for this is called the center. So the center in this one happens to be a 0, 0, but the center is HK, so it has a center, and that center is at HK. Okay, there is a distance from the center to a vertex. So there's two vertices on a hyperbola, these red dots. That distance from the center to the and happens to be in the horizontal direction right now. The distance from the center to the vertex is A. There's we should label an axis. Actually, I should have done that first. But this axis here is called the transverse axis. The transverse axis is not necessarily the longer axis. It's the axis that has both the vertices and the foci on it. So this one's going to have, it says foci, we haven't drawn yet, but it's going to be on this axis. And in this case, the vertical axis, it's not always the vertical axis. The other axis, the one that's not the transverse axis, is called the conjugate axis. Okay, I drew it up there, but really it's this. It's like, I actually need to draw this for something, so I'll draw right now. But this distance right here, okay, that's B. So 2B is the length of the conjugate axis. In this case, it's the axis that doesn't have the foci and the vertices on it. And then there's a final thing that's not on here yet, and that is the foci. The hyperbola has 2 foci, and the distance from the center. So like from the center to the focus, that's C. To either focus, that's C. And so what this definition here says is that if I picked any point, so if I picked, for example, this point right here, this point is xy. At any point xy that satisfies the parameters of the hyperbola, what it says is that I should have some more colors, but I don't. That this distance right here, we call that like D1. So from the focus to that, the two fixed point, the foci, those are right there. So that is distance 1, and then this distance, if I went all the way over here to the other focus, that's not drawn well, but that's D2. What this says is that the absolute value of D1 minus D2 is a constant. And so we're going to look at what that means really quickly, because there's a big long proof behind why something is the way it is for an hyperbola, but I'll show it in I'll show it in this video description, but I don't want to make a big proof out of it. We can examine one specific point here to figure out what this constant is. So that point we're going to look at specifically is actually a vertex. So if we look at a vertex, and we apply this thinking to it, well, what that means is that this distance right here, okay, which is, if we think about what A and C are, this distance right here is C minus A, okay, so that distance is C minus A. That would be like D1, okay, and then D2 would be D2 would be from the vertex to the other focus, right? And so that distance right there, which we just established, was C minus A, and then we have 2 A's, so this is A and this is A. So this distance is equal to, and this just happens to be really conveniently to choose it at the vertex, or either vertex, it'd be 2A, or so, sorry, let's fix this, I didn't do that right. It would be the absolute value of C minus A, that's your first one, then minus, we have C minus, we have the value of C minus A like plus 2A. And so that's like what we've got right there. So what's the absolute value of this? Well, we got to combine like terms on the inside, so it would be C minus A minus C plus A minus 2A. And then that's going to clean up to be just negative A. The A's cancel. It's absolute value negative 2A, which is just going to be 2A. And so we get this. So we get that constant is equal to 2A. And there's a big long proof for this, but what it tells us is that the relationship between A, B, and C is that C squared is equal to A squared plus B squared. So this is a very important thing for hyperbolas. And then the other thing, which is the standard form, the HK form or the conic form of a hyperbola, is this. It started off wrong. It is x minus h quantity squared divided by a squared minus y minus k quantity squared divided by b squared equals 1. Now this is almost the exact same thing as the HK form of an ellipse. It just has a minus sign in the middle instead of a plus sign. That's the only difference. One thing to note is that if the x term is positive, so x term, When I say x term, I mean this term right here. If that's positive, then the hyperbola is going to be like a left and right parabola. It's going to open to the sides. If the y term is positive, it's going to open up and down. So it's going to be one of those. So there's something to keep an eye out for. Okay, so we have a relationship between a, b, and c. We have the standard form, and there's this other thing that determines kind of the shape of how we draw the purple lines, and that is these like dotted orange lines that I drew in. So on the next slide I have a better representation of those lines. Okay, so here are those lines. Now if we kind of put some stuff back on this graph, this distance here, this is a, and this distance here, this is b. Okay, and this distance, this point right here, this point is hk. Okay, now if we wanted to come up with these asymptotes, these things are called asymptotes. There are lines that the hyperbola will come up to and not touch. It doesn't quite touch it. It kind of traces along it. It'd be good for us to be able to know the equation of those lines so that we can graph them. And it's actually really simple to do, because of the equation of a line in point slope form is y minus y1 equals m times x minus x1. So let's look at the slope first. Right, the slope of this is the rise over the run. So if we're looking at this one right here, what is m for this? Well, m would be the rise b divided by the run a, so it's just b over a. For this one, right, it's the same thing, except now the rise is b, but the run is like negative a, so it's negative b over a. So the slope is the slope for these asymptotes is either plus or minus b over a. So that's easy, because in all these situations we would have b over a. And then the other thing, if we want to just write one equation basically that describes both asymptotes, where we have a plus or minus for our slope, well, then we need a point that they have in common, and it's very convenient that these are always going to cross at the center of the hyperbola. So basically, in this case, x1, y1 is just hk for this. Like, that's the point that both of these lines will share. So the equations, so for all hyperbolas, the equation of the asymptotes, is always just going to be y minus h. Nope. Sorry. What? How come the eraser's not working? Y minus k is equal to plus or minus b over a times x minus h. And this is even more convenient than you think it is when we get to that. We'll get to that in a minute here. Alright, so let's look at a problem. Okay, this is the equation of a hyperbola, and it's not been given to us in a good form. One way we can tell right away that it's a hyperbola is that both x and y are being squared, and one of them is positive and one of them is negative. So it's squared. This is one of the terms is negative. Boom, it's a hyperbola. This is the only thing it can be. So we gotta put this in a more convenient form. We're gonna do that by completing the square. The y squared plus 6y is what it is. The negative 3x squared, the x is already being squared. There's no other stuff, so I don't have to worry about that. And this equals 0. So what do I have to add here? I have to add a naught to both sides, because that's going to allow me to have a perfect square trinomial right there. Minus 3x squared is equal to 9, and then we also want to divide everything by 9 because we want this equal to 1. And so what we have is y plus 3 quantity squared divided by 9 minus x squared divided by 3 equals 1. So right away the y term is positive, so I know this is going to be one of these. It's going to be an up and down hyperbola. I know that b squared is 9, so that means b is going to be 3. I know that a squared is 3, so a is going to be the square root of 3. And if I wanted to find c, which I do, c squared is just a squared plus b squared. So c squared is going to be 9 plus 3. C squared is 12. And c would just be 2 root 3 then. Okay, so that's A, B, and C. We have that. And now what we're going to do, we can get the center. That's one of the main things we're going to want for this. Okay, the center is HK. The center for this is just straight off of our standard form is going to be 0, negative 3. Okay. We also are going to want to know where the vertices are. And we're going to just quickly sketch something to see where the vertices are going to be. So let's put all this stuff on a graph first. We have 0, 3, that's the center. 0, negative 3, there's the center right there. Here we have, what else do we have? We have A, so we have, well, B. B is, where did I put B? It's 3. Okay, so B is 3. That means if I go 3 up from the center, I'll have a vertex. If I go 3 down from the center, I'll have a vertex. Okay, and then if I go A over root 3, which is about 1.7, okay, I'll have the endpoints of the conjugate axis. And I'm just gonna sketch in this that little box here. Sketch in this box. We'll have that dot. Sketch in this box. Okay, and then I'm gonna sketch in the diagonals of that box because those are the asymptotes. Okay. And I could even sketch in the whole hyperbola right now. Okay, so it's going to do this. I'm very bad at drawing these, especially on a computer. Who am I kidding? I'm just bad at drawing on period. It doesn't matter what the medium is. So I want to know the coordinates of the vertices. I already did the whole graph, but I know that it would be 3 up, or in this case B up from K. So if we wanted it in general for an up and down parabola, or for an up and down hyperbola, it would be H, comma K, and then plus or minus B. So for ours, for this one, it's 0, comma 0, and 0, comma negative 6. We also want to know where the foci are. And the foci are going to be 2 root 3 away. Again, root 3 is about 1.7, so 2 times root 3 it'd be about 3.4. So the foci are going to be like 3.4. They're going to be like in this area here. Okay, that one's a little too far, but it doesn't matter. It doesn't have to be perfect. So they are C away from the center. So this distance right there is C, and this distance right there is C. So if we wanted that in general, we would say that it's H, comma K plus or minus C. So for ours, then it's 0, comma negative 3 plus 2 root 3, which who knows what that is. Actually, it's, it's like 0.7. And then 0, comma negative 3 minus 2 root 3. So that's the center, the vertices, and the foci. We can label these foci. This one was the one that was 0, comma negative 3 plus 2 root 3. And this one was the one that was 0, comma negative 3 minus 2 root 3. And then the last thing that we didn't put is the equation of asymptotes. Okay, so remember, that was this, right? Y minus K equal to plus or minus B over A times X minus H. So we actually have Y minus K. It's this whole thing right there. And we have X minus H. It's this right here. It's this right here. So I don't even need to do any math here because I already have B. Well, I guess I need to put B over A. But I do have B and A already. B is 3 and A is root 3. So the answer to this, what is the equation of the asymptotes, would just be y plus 3 is equal to plus or minus 3 over root 3. And you can rationalize that if you want. We'll do that in a second. Times x. And that's it. Now we can rationalize this. We can say that this is y plus 3 is equal to plus or minus, what would that be? Would just be root 3, right? Yeah. 3 divided by root 3 is just root 3. And then that's just, wait, is it? No, it isn't. Root 3 times root 3 over 3. Yeah, that's right. X. or whatever. So that's it. We're done with that problem. Alright, I'll stop the video and I'll make a second video for this one.